So we'll take a look here at doing some analysis of the least squares regression line. In other words, how well does a line fit the data? So let's say we create a scatter plot with a shoe size and the height. So if you take a moment, put the, um, the shoe size into list 1 and the height into list 2, and then go ahead and create a scatter plot with that. Um, we can start to kind of come up with some of the relationships, talk about the least squares regression line, and then go ahead and start to interpret the slope and the y-intercept. So if you want to take a moment, pause the video, put that data in, go ahead and create the scatter plot, and what we should see is the following information. Um, One, when you look at that, you should get a strong positive linear relationship. The least squares regression line, once you do linreg, and we're doing the number 8 for linear regression. Make sure we go down to number 8. You don't want 4, you want 8. And then, so there's our line of best fit, 51.36 plus 1.87x. And then in order to interpret those, that's just using those templates we talked about yesterday. So the y-intercept of 51.36, that tells us when the shoe size is 0, the height is predicted to be 51.36 inches. Here, you can't have a shoe size of 0, so this is one of those y-intercepts. It doesn't have a practical application. The slope, right, at 1.87, that tells us that for every one increase in shoe size, the height increases by 1.87 inches. As your shoes get bigger, you get taller. Some of the data that you also get when you do the linreg is one of the pieces of data. You obviously get the R value, the A, and the B. You also get this R squared value. And what this is a coefficient of determination. And what that tells us is the percent of variation in the Y values that is explained by a linear model with X. And you can kind of use this as a template, just like we did for slope and y-intercept. That number, we're going to change that value, that R squared value, into a percentage, and then we're going to replace the words the percent with the percentage, the Y right there that I just underlined with the Y variable, and then the X right there with the X variable. And what it's telling us, so for our particular set of data before, we got a coefficient of determination of 0.8575. So what does it mean? Well, step 1, just plug it into that template we just saw. So 85.75% of the variation in height, right, this is our Y, right, is explained by the linear model, that's also important, of shoe size, which was X. One, go back to yesterday what we talked about in the previous video. We're talking linear or not linear. So we're not trying to fit like a quadratic model, a cubic model, an exponential model. It's just a linear model is the only one we're interested in for this particular course. So what that tells us is it looks like a lot of the variation that we see in heights can be explained by the differing shoe sizes. Not surprising that typically shoe size looks like a pretty good predictor for height. It's not going to be the be-all, end-all, and it doesn't mean that if I plug someone's height into that formula right there, the least squares regression line, that I'm always going to get the exact height that they have, because there's probably other factors that play into someone's height besides just shoe size. So what that tells us, a lot of the variation, again, explained by shoe size, but maybe genetics has something to do with it. How tall are your parents? Maybe weight has something to do with it. Maybe age has something to do with it, right? When you think you're going through middle school, maybe your feet get bigger quicker, and so maybe age is one of those other factors that we can put into that. So a lot of the variation is explained by shoe size. So it's a pretty good indicator, but if we maybe added a few other variables, we get an even better feel for how to predict someone's height. Going back to that line of best fit that we just kind of were talking about, right? We can fit that in there, and the idea, right, we have our prediction line. You can see there are going to be predicted values that are pulled from the prediction line, and the actual value, and the difference of that is error. Now, kind of what I just mentioned, if we try to predict someone's height using my least squares regression line right here, I'm probably going to get pretty close, but chances are if you plug your own shoe size into this model, and I think this is more for men's shoe sizes, so if you're a female and you're trying it, it might get your height exactly right, but chances are it's going to be slightly off, right? Chances are when we use our prediction line, which you see right there, to get a predicted value, there's probably going to be some type of error. There's going to be this gap between what it really is and what you were predicted to have, right? Sometimes the error is very big, like you can see in this particular box it's labeled. Sometimes you look at something like this and there's not much error at all. That means that that prediction, for this particular person, was when they plugged their value in, they got very, very close to what their true height was, maybe something like that. And so what those errors, another name for the errors, is a residual. And a residual is the difference between an observed value of the response value, variable, and the predicted. And you get the predicted by using the least squares regression line. So in terms of formula, it's y minus y hat. This is what's important, knowing this y hat. A lot of times there's questions, well, what does that really mean? Anytime you see the y hat, that means you're talking about something that is a prediction, right? So another way to think about this is some observed y value minus a predicted. So y hat is always associated with a prediction. So anytime you see those hats, we're talking about some type of prediction. Excuse me for writing like a 3-year-old. So how does that work out for us? Let's say here's our prediction equation, and we say, okay, I've got a shoe size of 8.5. What would my predicted height be? So we plug in 8.5, and we'd realize, okay, 67 inches. So about, what was that, 5'7". So with a size 8.5 shoe, I would be predicted to have a height of 67 inches. Well, if we go back to our original data, we actually had data on somebody that had a shoe size of 85 inches. And that person was 66 inches tall. Well, keep in mind that our predicted value was 67.25 that we just found. We found that value right there on the previous slide by plugging into the equation, right? So there's our predicted height of 67 inches. But we have an actual observed. But when I do observed minus predicted, I realize this person is actually just more than an inch below what is predicted. So the residual here for this particular individual is negative 1.25. They're about an inch below the predicted value. How that plays out for us, if we look here, here's that size 8.5 shoe right there. And this gap right here is about 1.25. And we're probably all aware enough to realize, well, we're below the line. That person was below the predicted height. So that's where we get the negative. The idea with some of this, if we were to add up all these different residuals, we see we've got 1, 2, 3, 4 that are negative, 5, 6 are negative, 1, 2, 3, 4, 5, 6 that are positive, and then a couple of these, right? A couple of these are sitting right on the line, right? Notice there are some that are pretty far above, right? Like this particular one is kind of far above, but then you also kind of have something that balances it here, kind of far below. And what we should notice, if we calculate all the residuals and add them together, right, some of those residuals should be 0. And that's one of the ways that calculators and whatnot figure out where to put that line of best fit, is they figure out where is it that I draw this line in order to get the residuals to sum to be 0. Calculator can do it a lot quicker than we can by hand. But if you kind of look at it, it on some levels makes sense what you're looking at. Let me erase some of these marks that I put on there, because we got a balance of some positives, some negatives, and some that are right on the line. And so when we add all those up, we should be 0. One particular type of plot that's really, really helpful for us is called a residual plot. And what that is going to do is basically just put all of our residuals. It's going to compare our original x value, right, which was shoe size, right? If you look right here at that axis, our x-axis here is going to be shoe size, and then it's going to plot it versus the residuals. And so again, our person that had an 8.5 size foot, we can see their residual was negative 1.25. So this gap from the 0 line down to the residual is probably right at 1.25. So they're about 1.25 below the line. Again, you see some are positive, some are negative. So in terms of analyzing a residual plot, because this is something you're going to be asked to do, you're basically looking for something that has no real patterns, no distinctive outliers, and a good balance between positives and negatives. You think about this for just a minute. When you draw your line of best fit, don't you typically, if you just estimate it, you'd put it where there's about the same number of points above the line of best fit and below the line of best fit, which means you get a good balance of positive residuals and negative residuals. Good way to tell a good residual plot sometimes is to look at a bad residual plot. And so these are all kind of bad residual plots because I could give you a pretty good description of what's going on. A is probably the closest to a good residual plot of any of these, but as you can see right here, as we get closer to the zero line, stuff really starts to concentrate. So I can give you a good description of what's happening right there with A. With B, we can see that it's a lot more concentrated in terms of the positive residuals, and it's a lot more spread out in terms of the negative residuals, right? I'm giving you a good description of what's happening. Part C, I can see this has kind of a parabolic shape to it. It's kind of a curve shape to it. I can see a definite pattern. And in part D, we can see it kind of spreads out as we move down the residual line. All of these have patterns. We look back at our previous example here. There wouldn't be really a good way to try to describe that, right? It doesn't look like a curve. It doesn't look like anything gets more spread out, less spread out as you kind of move down the residuals. There's no real pattern to this, making it a good residual plot. Your calculator will actually create residual plots for you, but this only happens after you have found the least squares regression line of the data. And this is because, if you think about it, well, in order to create residuals, well, one, we need to know how far away from the line are they. And the other thing that we need for residuals is we need a predicted value. And the way that we get that predicted value, okay, we need that predicted for observed minus predicted. Well, how do you get the predicted value? Well, you get that from plugging into the least squares regression line. So that's two reasons you need that least squares regression line. So in other words, before you can create a residual plot, you must find the least squares regression line. So step one for you, put your data in the calculator. Step two, find that least squares regression line. And then what you're going to do is put your residuals into list 3. So you'll go to your stat, edit your data, and make sure list 3 is cleared out. Go up and highlight L3, and then if you hit second stat, that's basically a big list of lists, right? If you look just above the stat button, it'll say list. So you hit second stat to get there, and you're going to scroll down. And what actually ends up happening is every time you run a least squares regression line, every time you do linreg in your calculator, it regenerates this residual list. So that's another reason why you get to the least squares regression line first. If you just put your data in and try to find residuals, it's probably a list of residuals from previous data. So you put data in, find the least squares regression line, then you can go find that residual list, drop it in a list 3, and then that scatter plot doing L1 versus L3 is going to plot your X values versus your residuals, and you can take a look at whether or not you have a good residual plot.